All right, how we doing this Monday? Snow over the weekend, always kinds of fun. Couple things. I did this later in the day. I got some grades updated into School Tool or whatever those assessment qualifiers are. Just letting you know, there are some people that I know that play football, volleyball. I think it's football and volleyball that are players on the teams. You guys are not eligible as of right now, according to chemistry. So just be aware of that fact. A couple of you aren't doing hardly anything. So it is what it is. It's a choice by you to do that. You're doing some things, but not everything, and you're not doing it to your best of ability. Averages. The district still hasn't told us how we're doing final averages for the year. Basically, I told you before that marking period 4, I'm going to keep a separate grade book and then just translate it to their complete and meeting standards, complete approaching standards, and complete and missing. Missing is basically 40 and below. Incomplete is 41 to 64. Complete and approaching is 65 to 80. And meeting standards is 81 and above. All right, so that's kind of how I just translate it. I just do it week by week. I take all the assignments for the week. Last week I think there was 3. This week there might be 4. And then just average them out, come up with the normal grading thing, and then average it out and just put in one assignment into School Tool. So just letting you know that we are an organic. I will be checking your work that you did that was due today after I record this. You're going to need to make sure you practice with this stuff. This stuff is a little bit of a challenge. If you just look at it superficially, you're not going to get it. But, the more work you put into it, the more you're going to get out of it. It's kind of the same thing that we talked about all the time in there. Okay, so bell ringer here. Not going to leave it up long, so draw the structural formula for 2-octene. What is the molecular formula? All right. Okay, so molecular formula. So oct means 8, ene means there's a double bond. 2 in front of it just means where the location of the double bond is. So molecular formula is C8H16. C8H16. If you were to draw the structure out, now I wanted to show you this because this is when you do go to college. They don't write all the carbons and hydrogens. So every one of the ends of these lines represents a C and its respective H's. So this carbon here would be a carbon with 3 H's. This would be a carbon with 2 H's because it's got a carbon going here, a bond going here and a bond going there. So it's going to have an H up and an H down, so it's going to have 2 H's. This is going to be a CH2, this is going to be a CH2, this is going to be a CH2. Now here's where the double bond is. It's after the second carbon. So if you look from this side, second carbon. All right, it's just going to have the 1 H. That's it. That's why I only have 1 H going off of it. And down here, you'd be a CH3. So if you wanted to count those up, you would get CH816. You could do the formula CnH2n. All right, but either way, it gives you that structural formula for that. All right, some general properties of organic compounds. I'm going to kind of roll through this kind of quickly because I talk about them as we get to them and different things, but everybody likes lists, or seems to be anyways. All right, organic compound, because they have carbon involved with them, are going to be covalently bonded. You cannot get an electronegativity difference greater than 2 with carbon, so therefore they're all going to be covalently bonded. All right, there might be an ionic bond on the end of one, but generally classification, it's covalently bonded. All right, generally speaking, because they're covalently bonded, they're going to have low melting points because the bond is fairly weak. All right, covalent bonds are not strong bonds. All right, so that's going to result in lower melting points and also boiling points as well. They are non-electrolytes, generally speaking. There are some exceptions. We'll talk about them when we get to functional groups. But if you remember what an electrolyte is, it's something that conducts electricity in solution. What gives it the ability to conduct electricity in solution is ions or charged particles that can move around. Covalent compounds, because they're covalently bonded, don't produce ions. All right, remember, ionic compounds produce ions. All right, so generally speaking, covalent compounds do not conduct electricity. Generally speaking, they are non-polar. All right, remember, kind of our like dissolves like thing. Generally speaking, organic compounds will not dissolve into water. Think of gasoline, oil. All right, those things do not dissolve into water. They are non-polar. We know water is polar. If you know nothing else, water is a polar molecule. So if it doesn't dissolve into it, then it is a nonpolar substance. There are exceptions to this. Alcohols are organic compounds. They dissolve into water. Sugars are organic compounds. They dissolve into waters, but we'll talk about those when we get to those. All right. Because they are covalently bonded, they are going to react relatively slower than inorganic compounds. Inorganic compounds, generally speaking, have already broken apart into ions, so they just have to reform new bonds. That's a one-step process. These things, because they have to break bonds and reform new bonds, you can kind of think of it as a two-step process. That's going to make them a slower reaction rate or give them a slower reaction rate. So compared to inorganic compounds, they are slower. All right. Because they are slower, one other reason is because they have high activation energies. Remember, activation energy is the energy needed to get it started. All right, it's the energy needed to break the bond, so to speak, that hold it together. So they do have higher activation energies, so that cause them to react slower as well. All right, generally insoluble in water, and that piggybacks this one up here in that they're generally nonpolar. Okay. So hydrocarbons, remember hydrocarbons? Hydrocarbons are compounds that contain hydrogen and carbon only. Last lesson, we talked about alkanes, alkenes, and alkynes. We talked about what are called straight chain hydrocarbons. Basically one line of carbons, you count up the carbons, you find out if it's got single, double, triple bonds between the carbon atoms, and you add an ane, ene, or ine respectively. Remember, anes are single bonds, enes are double bonds, ines are triple bonds. All right, today we're going to deal with what are called branched hydrocarbons. These can look scary, but they're generally not too bad if you take the time and break them down. All right, and then up here, this word nomenclature, that's just a big fancy word for naming. All right, so this is how you name, or it's the nomenclature for organic compounds. All right, okay, so branched hydrocarbons. So you're going to look for the main piece and then the branches off of it. All right, so right here. So names are made up of side chains and a base. So if we look at this molecule right here, all right, it's got 1, 2, 3, 4, 5, 6 carbon atoms. If you were to name it like we did last class, you would see 6 carbons as hex. All right, they're all single bonds between the carbon atoms, so that'd be hexane. But this is not hexane. This is something called an isomer of hexane that we'll talk about in a little bit. All right, but it's not hexane. All right, so you got to find the longest chain of carbons that you can. I'm going to use my mouse pointer. You'd use your finger, your pen, or pencil that you can run along and get without picking it up and moving it to some other place. So I'm going to show you right here. I can go 1, 2, 3, 4 that way. I can go 1, 2, 3, 4 this way, or I can go 1, 2, 3, 4, 5 from left to right, or I can go 1, 2, 3, 4, 5 from right to left. All right, so the longest main chain of carbons, or the base as we're going to call it, is 5. I'm going to color, I think this color codes it. Yep, so now the base is color coded this kind of funky green color. I don't know if you can appreciate that, but you can definitely see the red color. All right, and I colored the side carbon in this case. I don't know why I'd colored the hydrogens, but just to show they're associated with it. All right, the side carbons in this case is a 1 carbon. All right, so the base, we named the base like we learned last class. All right, you count up the carbons, see if it's got to have, if it has a double or triple bond in there, you've got to put the double or triple bond in the base. All right, and then we name it accordingly. So here we've got 5 carbons, 1, 2, 3, 4, 5. All right, they're all single bonds between the carbon atoms. So 5 carbon prefix is pent. All single bonds means ane. So the base name of this thing is pentane. All right, then we are going to look at the side chain. So here's our side chain. All right, so our side chain in this case is how many carbons big? It's 1 carbon big. All right, we know a prefix for 1 carbon means meth. All right, when you have a branch, when the meth is a branch, or the eth is a branch, or the prop is a branch, or the non is a branch, whatever branch it is in terms of numbers of carbons, branches always end in YL. So this is methyl pentane. Meth because it's a 1 carbon branch. Pentane because it's 5 carbons in the base chain. It's the longest chain of carbons you can get. Now, if you had 2 carbons coming up to the top, it would be ethyl. If you had 3 carbons coming up, it'd be propyl. All right, if you had a carbon going up and a carbon going down, it would be methyl-methyl. We shorthand that to dimethyl, but I'm not going to worry about that. So it'd be methyl-methylpentane if you had 2 carbons coming off the same carbon, or a methyl coming off a different carbon. All right, the only other thing we have to do is we have to identify the location of the branch. So we know that this is pentane, and then we have to count up to see what carbon the methyl branch is off of. So 1, 2, 3 from the right side, 1, 2, 3 from the left side. It doesn't matter, they're both going to be 3 in this case, so we get the name 3-methylpentane. If they both weren't the same number, then you would have to pick it so that it comes from the shortest side, or it makes the number the smallest number possible. All right, and we'll see some examples with this. So the true IUPAC name, so to speak, for this compound is 3-methylpentane. All right, pentane meaning 5 carbons, methyl meaning that one carbon branch comes off the pentane, and then 3 telling us the location of that methyl on the pentane, which carbon it comes off of. Okay, all right, there's a lot in there. All right, so the root or the base is as long as possible carbon-hydrogen change. So in this case, the base is 5 carbons long. All right, if there's a double bond in here, like if this one had a double bond up here, this would have to become part of our main chain or our base chain. We have to incorporate the double bond. We're not going to deal with double or triple bonds in side chains or in branches. All right, anytime you have a chain, you change it to YL. So methyl, ethyl, propyl, butyl, pentyl. All right, we will deal with halogens being chains, like chlorine, all right, or iodine or bromine, and those are going to be bromo, chloro, iodo, fluoro. All right, so right now the carbon chains, they're going to be end in YL. All right, so here, methyl is going to be a 1 carbon chain. Ethyl is a 2 carbon chain. All right, propyl is a 3 carbon chain. If you've ever heard of isopropyl alcohol, it's a specific orientation of the 3 carbons off of it. All right, so that's isopropyl. It doesn't, we don't have to know isopropyl. I'm just doing this for the numbers of carbons and just showing you some other things, because if you do read bottles or read labels, then at least you have some idea what it is. All right, and that's what isopropyl looks like. I'll come to here. All right, so it's connected, it's a branch somewhere off of something, and then you got 3 carbons, and it's bonded in the middle carbon. That's all it means. All right, if you have a halogen, all right, bromine becomes bromo, chlorine becomes chloro, fluorine becomes fluoro, iodine becomes iodo. Now, I'm talking fast through this. There's no way you can write this fast at it. I'm going to stop and put questions on Edpuzzle, but I'm doing it so that the video is not as super long. Okay, so those are branches. So now we're going to whack you with I think it's a pretty hard one, or a pretty long, complicated molecule. Haha, here we go. All right, so you're going to stop and write it down. All right, I would pause this, and please write it exactly how it's written. If you were to make it, I don't know if this really appreciates it, but this is what it looks like. All right, this is kind of a big, complicated thing in terms of 3-dimensional structures or whatever. We've drawn it in 2 dimensions on the screen here. All right, it's 3-dimensional here. I just can't get far enough away to give you a good appreciation for it, but I did make it. I did use up all of my carbons and hydrogens, though. Okay, so what I want you to do now is to find your longest chain of carbon atoms. All right, where can you get your longest chain of carbon atoms? All right, so once again, now you're going to have you pause it. All right, I'm just going to go with it. So, you can go this way and you get 1, 2, 3, 4 that way. That's really not that long. All right, we can go with yellow. We can go 1, 2, 3, 4, 5, 6, 7 that way. All right, we can go, no, I already did that blue. Sorry, I'm trying to change color. Purple. Let's go 1, 2, 3, 4, 5, 6, 7, 8. All right, I don't think we're going to get higher than 8. So 8's going to be the winner, so to speak. All right, so our main chain of carbons here is this. Is 8 carbons going, well, I'm just drawing a line through it. See, notice how I'm not picking up my thing and going back and going somewhere else and drawing it in. So that's my longest chain of carbons. All right, so what's our prefix? Now, one thing I forgot to ask you, does this have a double bond, triple bond, and here are all single bonds between the carbons? They're all single bonds, so the end name of this is ain't. So I can start with that right here. Let's see if I can write with a mouse. Writing with a mouse is a challenge for me because I'm left-handed. So the ending of the name is going to be ain't. Okay, so it's going to be ain't. Now, how many carbons long is it? 1, 2, 3, 4, 5, 6, 7, 8. All right, so 8's prefix is oct, so it's going to be octane. So probably writing this too big for the name to actually fit on here. So octane. All right, so we get octane in there. Perfect. All right, but what does that not take into account? That does not take into account this carbon, nor this carbon, nor this carbon. All right, notice I circled the carbon, so I have 3 different branches here. I have a branch here, I have a branch here, I have a branch here. All right, how many carbons long are these branches? They're each 1 carbon long, so this branch here is called a methyl. Yeah, this is where, I'm gonna see if I can do it. Move the mouse to my left hand, see if I can do it this way. Never used a mouse. Probably not gonna be much better. All right, there's a methyl. Here's a methyl. Sorry about the poor writing. Yeah, I can't really write, but that's fine. I actually write better with the mouse with my right hand. And then here's a methyl. So our technical name of this would be methyl, methyl, methyl octane. But that doesn't give us enough information. So I'm going to write this out. So we got methyl. Don't laugh at my writing. I don't laugh at yours. I do have a touch screen, but I don't know if it'll... Oh, this is awesome. I just realized. So I can at least write quicker. Methyl, methyl. So this would be messy. Methyl, methyl, methyl octane. Now, we have to deal with numbers. All right? If I go from this side, this carbon would be 1. This would be 2. This would be, let's see if I can do this, 3, 4, 5, 6, 7, 8. If I go from the other side, I'm just going to change colors. Let's go with this blue. You get a 1, you get a 2, you get a 3, you get a 4, you get a 5, you get a 6, 7, 8. Now, this is a super complicated molecule. I do hit you with a hard one here because, you know, I might as well do a hard ones with me here. So now let's look here. So if we go with the red, or let's go with the blue because I've got that color written up here. We've got a 3. So this would be a 3. This would be a 3. And this would be 1. This would be a 6 methyl. If we went with a red, if we go with red, we've got a 3, 4, 5, 6, 6. So which one's going to make a smaller number? 336 or 366? All right, 336. So we got to go with the blue ones. All right, so I'm just going to go back to the blue color. So we've got, it doesn't matter which ones you go 3 methyl, 3 methyl, 3 methyl octane. All right, so that's the technical name for that one. If you want to get fancy and do what you might see, I don't know if I would ever write it out that way. It would be 3, 3, 3, comma, 6. I would call it, oops, I said it wrong. Not dimethyl. It'd be 336 trimethyl octane. I feel like I'm writing like some of you guys. I apologize. All right, 3, 3, 3, or 6. This is a 6, sorry. Trimethyl octane. Okay, so that's the big fancy name for this. I'm going to click through these slides because I built the PowerPoint to do in class and for people to be able to do it at home. All right, so if we go through here, we're going to get the same name. This is just going through, oops. All right. So here we go. So now we got to name these puppies. Okay? All right, so up on here, and I don't know if you really want to draw these out or if you want to just kind of follow through. I would recommend drawing them out, trying to find the, could I go one at a time at these or do they come in? All right. So here, you find your longest chain of carbon. So I'm going to go through here and I'm going to draw so I'm going to call this molecule 1. This one's going to be molecule 2. This is going to be molecule 3. All right. So in molecule 1, what is your longest chain of carbons? I'm just going to draw a line through it. So you got carbons right here. Okay. So you end up with that many. Now, which ones did you not include in there? And this is what I do is I literally draw a line and then I circle the branches. So my main chain here has got 1, 2, 3, 4, 5, 6 carbons. So that's hex. They're all single bonds, so it's hexane. And then I've got a methyl group off it, so it's methylhexane. What methylhexane is it? If I count from the bottom, it's 1, 2, 3, 4, 5, 6. So it'd be 4 methylhexane. Or if I count from the top, it'd be 1, 2, 3. Because the 3 is smaller than a 4, we have to go with that as its name. So the name of this thing should be, if I can get through to this, is 3-methylhexane. Okay? All right, so that's molecule 1. I'm just going to erase the ink, make life easier to see. All right, so up here, what's your longest chain of carbons that you can get? You can get 1, 2, 3. You can get 1, 2, 3, 4, 5, 6 that way. You can get 1, 2, 3, 4, 5, 6, 7 that way. So 7 is definitely our longest chain. And it doesn't matter, and I went from here. It doesn't matter if you go from the left or the bottom. You're still going to get the same number, 1, 2, 3, 4, 5, 6, 7. So it's still 7. All right, it's fine. Your branches this is a branch. That's a 1-carbon branch. This is a branch. That's a 2-carbon branch. So this branch name would be methyl. This branch name would be ethyl because it's 2 carbons. So this is a meth. This is an M. I'm just going to put an M. This is an E for ethyl. All right, so we've got a 7-carbon, all with single bonds. So it's heptane. And then we've got methyl, ethyl, heptane. Now, the only other thing we do have to add in is the numbers, which way to number to orient it to make it smaller or the lower. If I go on this side, it's 2, 3, 4. So it's 2-methyl, 4-ethyl. Or if I go from this side, it's 1, 2, 3, 4, and 6. So 4 and 6 definitely not going to work. So we've got 2-methyl, 4-ethyl, and what did I say it was? I forgot. Yeah, heptane, 4-ethyl. And the reason why we want, yeah, that's not right. That name's not right. Too funny. That's not good. It's not dimethylheptane. It's just, it is just 2-methyl, 4-ethyl. All right, so I'm going to cross out this. This is not right. Just go with the name that I said. Okay? All right. And then our last one down here, our longest chain goes straight across. 1, 2, 3, 4, 5, 6, 7, 8. So that's octane. We got a 1-carbon chain and a 2-carbon chain. So we got a methyl and an ethyl, or ethyl and methyl. It doesn't matter. All right, we're going to go from this side. So you get 2-methyl. 1, 2, 3, 4, 5. 5-ethyl octane. Yep. Okay, and I put ethyl first because alphabetical, it doesn't matter. You can go 2-methyl, 5-ethyl, or 5-ethyl, 2-methyl. And I know it's talking in gibberish right now for a lot of you, but it does not matter which one comes first, ethyl or methyl. All right, it's not going to matter. All right, so isomers. So do I want to go into any more? Yeah, we'll start isomers today. Isomers are compounds that have the same molecular formula but different structural formula. So if you look here at this picture up here, you've got 1, 2, 3, 4, 5, 6, 1, 2, 3, 4, 5, 6, 7 carbons that way. This one's got 7 carbons oriented in a completely different fashion. Okay, so basically these are 2 completely different compounds. The only thing they share in common is that they have the same number of elements. They have the same number of carbons, they have the same number of hydrogens. Because they have the same number of carbons and hydrogens, they're considered to be isomers of each other. All right, they're images of each other. These ones it gets into something higher level in chemistry called chirality. We're not going to do that at this level, but it goes along with isomers. All right, so isomers, same structure, all right, or different structure, same molecular formula, same number of atoms. Okay, so I forgot, I'm on the little, there it is. All right, so structural isomers. All right, so here we go. These are isomers that have 4 carbons and 10 hydrogens. All right, so pause the video, write these down. Now I write CH3. This really means this, C with an H here, with an H here, and with an H there. And then a CH2 is just going to be a C with 2 H's off of it. Okay, so I do that. It's easier to fit on a screen, is why we do that. So this has got a CH3, CH2, CH2, CH3. This got the same thing, or a similar type thing, just arranged differently. All right, so this one's a straight chain. You can get all 4 carbons in one chain. This one, we cannot get all 4 carbons in one chain, no matter what we do. So this one's 4 carbons, single bonds, so that's butane. All right, and then the other one is just going to be called methylpropane, 2-methylpropane. They both have the same carbons, same hydrogens, just different orientation. All right, which means they're not going to have anything in common other than the number of elements. That's it. All right, we got more that we can get with this, though. All right, this is 1, 2, 3, 4. These two, I didn't put the number of carbons and hydrogens for this next ones. All right, these have 4 carbons and 5, 6, 8 hydrogens. So this one has 4 and 4, 8 hydrogens. So it's C4H8. So this now has double bonds in it. So but notice the location of the double bond makes it an isomer. This one is called butene, as is this one, butene. But they're not the same because they don't have the same location of the double bond. We just put the number in to locate the double bond. So this is 1-butene. This is 2-butene. Okay? So they're different because of the location of the double bond. All right, these ones down here, we're not going to really worry about naming them. They're ring structures. We're not going to get into naming ring structures, but these are all different variations that have the same number of carbons and hydrogens, but different numbers or different arrangements of them. So they all have 4 carbons. These ones have 5. These ones have 8. So these are actually isomers of these ones up here, of the 1-butene and 2-butene. All right. And because those are different isomers, all right, I'm just going to give you the names. I could care less about the name. Methylpropane, cyclobutane, and methylcyclopropane. We're not going to get into naming anything like that. All right. And then just a quick briefing of next class. I'll do this slide next class. But notice what else we can get isomers with is the location of, we're going to introduce in other elements next class. And these are going to have 3 carbons, and they're all going to have 8 hydrogens and 1 oxygen. Or 1, 2, 3, 4, 5, 6. Yeah, it is 8 hydrogens. All right. But where the oxygen is changes it. Like this one is an alcohol. This one's an alcohol, different alcohol though. All right. And then this one is an ester. Or an ether, ether. I said the wrong word. All right, so it's just what it is in location. Different, it just can be arranged differently. Okay, we are done. All right, please, please, please do the work for this. Okay, talk to you later.